All right, we're going. If you want to take out your highlighter, you can highlight what is an infinite geometric series, has an infinite amount of terms. And sometimes you can add them all up. For an infinite geometric series, if the sequence of partial sums converges, and then there's a finite sum. So we saw that when I walked to the wall. There was a finite sum. We saw that with the squares being cut and only having a third shaded each time. The key to figuring out whether or not something is going to have a finite sum is based on the R value. So in A, we have an infinite sum. The 3 dots at the end of the series tell us that this continues on forever. One of the things that we're going to find out is that sometimes that sum will get closer and closer to a value. And what we're looking for, just like when I walked to the wall, right? After 25 days, what was the distance I was walking each time? It was so small, you would basically say it's basically 0. So if the terms become closer and closer to 0, then you're going to get a finite sum when you add them up. Because eventually, you're not adding anything to the number, and you have your sum as a total. Okay? So does the first one look like the numbers are getting smaller and smaller? Yes. So the terms, we would say, are approaching 0. This has a finite sum. If we wanted to predict it, we could take out our calculator, have it crash. No, there we go. And we could type in what is 1/3 plus 1/12 plus 1/48 plus 1/192. We're already at 0.4427. If, what would be, do you notice that the bottom is getting multiplied by 4? So the next one that I would add, I could take this, I would add 1 divided by, and on the bottom I could take 4 times 192. And now I'm at 0.444. And if I added the next one, plus 1 divided by bracket, well, it would be 4 times 192 times another 4. And we're at 0.44335. Which numbers are changing? Okay, if we compare them, notice the first 0.4 has never changed. So my guess is that it will never become 0.5. Okay, looking now that then the second 4 has never changed. Now the third number changed. But do you think it'll go higher than 4? Maybe, maybe not. We could add some more numbers to check. What would your estimate be? Maybe. 4 is forever? The answer to that is going to be yes. But I can't. We'll find out in a little bit of anticipation, a little bit of drama happening right now. Second one. Oh, by the way, can you see in the first one that in the geometric sequence, we would say that our R value is 1/4. You're multiplying the denominator by 4, which means the whole fraction is getting multiplied by 1/4. And we say that something converges if the terms go to 0. Can you see when you multiply by 1/4? I could have done the same walking thing and got to the wall technically faster if I always walked 1/4 of the distance. Right? Instead of walking 8 to begin with, I walked 12. And then there was 4 left, and then I walked 3 of them. And then there's 1 left, I walked 3/4 of it. And so on, and always walked 3/4 of the way there. I would get to the wall technically a lot faster, but would I ever get to the wall? No. So, that's pretty cool. So what did we just figure it out? We just figured out that 8 plus 4 plus 2 plus 1 plus ... forever equaled 16. And I just figured out if I started with walking 12 plus 3 plus 3/4 plus 3/16, it's also equal to 16. Just a different way of getting to the wall if I did that forever. Okay, very cool. So, second one. Are the numbers getting smaller? We go from 4 to 8 to 16 to 32. The next one will be 64. Numbers are getting bigger. We would say this series is divergent, not convergent. Convergent means it approaches another number. This one doesn't. So if it doesn't, we would say there is no finite sum. And if we look at our R value here, we are doubling each time, so our R value is 2. Does it make sense that when R is 2, things got bigger? Hence, they're not going to be divergent. But when R was 1/4, things got smaller, and we approached a number. Do the numbers look like they're approaching 0 in the last one? They seem like they're getting smaller. So with this last one, we would say it has a finite sum. If we looked at our R value, can you see that you're multiplying the bottom by 10? So your R value would be 1/10. Oh, it's actually switching between positive and negative, so your R value is actually negative 1/10. So we're adding then subtracting, then adding then subtracting. If we look at our calculator and do an estimate of what this does, so we have start with 1/10. Then we subtracted 1/100th. Then we added 1/1000th. Then we subtracted 1/10,000th. We're currently at decimal 0909. Next, we would add 1 divided by 1, 2, 3, 4, 5 zeros. Boom. 1.09091. Then we would subtract 1 divided by 1, 2, 3, 4, 5, 6 zeros. And we have decimal 090909. Do you think the next one's going to be decimal 090991 and then decimal 09090909? And so on and so forth. So our estimate, which is actually going to be correct, it's going to be 0.09 repeated. Oh, okay. I am trying right now to hold back because I have like a whole bunch of math that just wants to come out and show you stuff that's really cool. We can maybe do a little bit of it, okay? Does anybody know how to change this to a fraction? Does anybody know what fraction is decimal 09 repeated forever? I do. Does anybody here know? Okay. Decimal 09 repeated forever. is 1/11. Okay? Decimal 4 that we had earlier, oh my goodness, repeated forever is 4/9. Did you know that? Did you know that decimal 0.9 repeated forever is also 0.9 over, well, you don't have to write 0.9 on top, but it is 0.9 over 99, or 9 over 99. Can you see that 9 over 99 is the same if you divided them all both by 9, 1/11. Did you know that 7/9 as a fraction is 0.7 repeated? What do you think 8/9 as a fraction is? Yes, 0.8 repeated. What do you think 13/99 as a fraction is? 0.13 repeated. Any ideas what 123 over 999 is as a decimal? 0.123, 123, 123, 123, 123, 123, forever. Fascinating. Okay, so that's all pretty interesting. So now the question is, we can do estimates, but how do we actually come up with this with a formula? Okay? Because what we were doing is we were adding a bunch and looking at the answer and hoping we'd see a pattern. When you're adding up a geometric sequence, we have a formula. And that formula was that the sum of your first n terms was term 1 times 1 minus r to the n over 1 minus r. And we just said if r is technically, we'll write it this way, technically between, not even equals, take those away, technically between -1 and 1, like a third, or negative a third, or a quarter, or negative a quarter, or a tenth, or -1/10. It makes sense that if we are multiplying by a fraction, making it smaller, that in the sequence, the numbers get smaller and smaller, eventually go to 0. Okay? We found that out. And so we found out that if they get smaller and smaller and smaller and eventually go to 0, then the sum converges to something. Now, this is beautiful. We're going to now look at this formula, and instead of n, we're going to put an infinity there, saying it goes on forever. Will term 1 change if you looked at an infinite amount of them? No. Term 1 would still be there. You would then have 1 minus, and then r would have an infinity up here. And you'd have 1 minus r. So let's take an r value on our calculator and check. Something between 0 and 1. We started with, let's start with our square with the shaded parts. There, our r value was 1/4. Let's put 1/4 in brackets. 1 divided by 4. And let's put it to a very big number, because there's no infinity button on your calculator. Let's choose a very big number, okay? If you were in kindergarten. If you were in kindergarten, would like 10 be a big number? That's a big number for you? Okay. Okay, we'll start with 10. Look how tiny it is already with a big kindergarten number. Do you know what this e to the minus 7 means? That means there's like 1, 2, 3, 4, 5, 6. The 7th number is where your number started. That's already pretty close to 0. Okay? Now, it probably didn't take you very many, like in grade 2, what were big numbers for grade 2? What would you, like, are grade 2s already in the millions? Or would they be like hundreds as big numbers? So we change this to 100. Now there's 61 places that decimal place got moved. That's really close to 0. And we're only at 100. How big is infinity? Like, as a concept, we're saying bigger than big. Like, bigger than a million, bigger than a billion. If your calculator can't handle it, let's see, I'm really curious. At what point does my calculator say I can't handle it anymore? Right? Do you think it can handle 1,000? We'll check. Because technically, you should know that it shouldn't be 0. It should be close to 0. But if I put in no, it can't handle 1,000. And different calculators, this is also terribly interesting, different calculators can handle different amounts of numbers. So some, like if I went to a calculator on the computer, it could do the 1,000. And it would tell me what it is. Here, you want to see? The best math thing on the internet is something called Wolfram Alpha. Oh, perfect. This is a great day to be slow. Wow. I want to show you something interesting. Okay, will it let me click on that? Yes, okay. What was I saying? Okay, Wolfram, I was saying that you were very impressive, that you could do this. Yes. It not only decided to simplify the bottom for me and write it as a fraction, it also decided that if you wanted a decimal, it's times 10 to the negative 603. So you can imagine 602 zeros and then the 8. I hope you can see that that is very, 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 very small and very, 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 very close to 0. Okay? Now, this whole process of what we've been doing is to tell us that theoretically, if you put an infinity in here, this is basically 0. Your calculator already said it's 0 at 1,000. I am now curious at what point I can make Wolfram Alpha start to cry and just say it's 0. I don't know what the calculator's actual one is. It's probably something inappropriate like 666 or something, sign of the devil or crazy. That's happened before, I can tell you from experience. But let's see. Do we make it cry? Oh, it didn't do it's sort of crying at 100,000. It decided not to do the decimal places, but it changed it to a 10 to the power. So it's kind of still able to do some math. Right? Oh yeah, you want It's not happy. Shoot, I'm going to crash the system. Can you see it's like shade things are moving? Yeah, we'll see what it's doing in 25 minutes. But I might have just hurt its brain. That wasn't nice. But all of that comes down to the fact that if this is 0, then in the brackets I have 1 minus 0, which I can do pretty good mental math. That's just 1, which means the top is term 1 times 1, and our formula for an infinite amount of numbers is actually easier than our regular formula. So now let's take our formula and redo the things that we started with. The first one with the boxes, right? The first one with the boxes was saying you had a quarter shaded, and then you added a 16th, and then you added a 64th, and you did that forever. Your R value is 1/4. Your term 1 was 1/4. Plugging that into our infinity formula, we would have 1/4 divided by 1 minus 1/4, which is 1/4 divided by 3/4. Do you remember how to divide fractions? You multiply by the reciprocal, so this would be 1/4 times 4/3. My 4's nicely simplified, and sure enough, mathematically I get 1/3, which we saw in the picture. The next one that we did is I walked to the wall. I started walking 8 blocks, then 4 blocks, then 2 blocks, then 1 block, and on forever. My R value was always a half. My term 1, I started walking 8 blocks, 1 minus 1/2. This would be 8 divided by a half. How do I divide fractions? The first top fraction is 8/1 multiplied by the reciprocal. And sure enough, I get 16. And our sum formula turned into a very simple, elegant, infinite formula. Okay, that was video 1. That was